Well, Steve, thank you very much for this invitation. It's a little intimidating to speak for the soil health community since I'm actually a geologist. I came to looking at soils from sort of the bottom up, from a very different perspective than a lot of soil scientists may have. And I'm going to try and talk very fast because I've got a lot to cover in a half hour. And my conflict of interest is on the screen at the moment. I'm also a writer, and I encourage all of you to read my books, obviously. But I want to start with a quiz. I mean, as a professor, I get to do that, right? So which planet is healthier for people to live on? The blue one or the red one? Well, we all know the answer, right? It's the blue one. Why? Well, you can see it. There's water on it. You can see the atmosphere through the water vapor. But the thing that shows up the least on that image is the little patch of brown stuff in the corner. There's soil on Earth. It's actually fundamental to life on the continents, and it is foundational not only for human health, but for the health of organisms that live outside of the oceans. So when we think of planetary health, we've got one planet we know of that has soil on it. So what's the state of the soil? You saw a slide a moment ago of the sort of degraded state of part of the world's soils. I won't repeat that slide, but there was a UN Global State of the Soil Assessment a couple years ago that in the executive summary advertised that humanity is losing about 0.3% of our global food production capacity each year to soil erosion and soil degradation, the loss of the soil itself and the degradation of its ability to grow food. Now, 0.3% is kind of a small number. It's what we're getting at our savings accounts these days, right? But if you think like a geologist, run that over 100 years. That adds up to 30% of our global food production capacity if we continue on the path that we're on at the pace that we're degrading the world's soils. And it's my contention that agriculture is going to need to change in the next 100 years, and I'm very interested in exploring the connections to human health, not just from the food production problem, but from the kind of things we'll go in as well. And this is a problem that has a history behind it, because if we look back at the development of agricultural societies around the world, which I did for a book called Dirt, the Erosion of Civilizations about 10 years ago now, that got me thinking about soils as a geologist. If you look at the history of societies, you can boil basically a lot of that down into societies that did not take care of their soil, did not take care of their land, did not last. Because soil erosion played a key role in the demise of civilizations going all the way back to Mesopotamia, Neolithic Europe, classical Greece, Rome, the southern United States. I talk about all that in the Dirt book. The common element there was essentially what you see still happening today in parts of the world, where this shows you what happened in a part of Costa Rica that I visited in writing my more recent book that shows that the change in the soil under about 100 years of coffee farming on steep slopes in that region. So the one that's on the left side of the screen that has the notebook in it, that's the soil profile that you get if you dig into a road cut on the side of a road up in the native forest. And you'll notice there's a bunch of dark stuff above the lighter stuff below. That's topsoil. That's where the fertility of the land is essentially kept, if you will. The slide on the right, that is a coffee plantation that's been managed for about less than 100 years. You'll notice that the dark stuff on top is gone. The subsoil is right to the surface. This is not an unusual pattern. You can see this all over the world if you know how to look and know where to look. And it actually affects the agricultural productivity of the land. And it also affects, it's not limited to tropical areas like Costa Rica. And again, in the Dirt book, I go through all the societies I could find where you could make this story. I want to emphasize that the history of the United States actually involves the problem of topsoil degradation and erosion as well. This shows you a map of the historical erosion in the Piedmont region, the upland or hill country, extending from Virginia up there in the upper right down to Alabama in the lower left. And you'll notice that gray noodle, which is that Piedmont, the upland country, there's 4 to 10 inches of topsoil loss across the region. The black areas are where there's been more than 10 inches. Well, is that a big deal or not? How much topsoil do you think was there to begin with? You go back and you read the original journals of a lot of the early plantation owners who were first farming these fields, and there was only 6 to 12 inches of rich black earth over the subsoil to begin with. And if we've eroded off, a third to all of the topsoil across a region that was one of the original breadbaskets of the American colonies, and we did it in 200 years, think what the Greeks could have done with a 1,000-year run at southern Greece. Think what the Romans could have done with an 800-year run at central Italy. This story has been repeated all around the world many times, and it has had great implications for the societies that developed in those areas. What does this look like on the ground? Well, if you go into North Carolina into a region in that gray noodle that I just showed you, and you go to a tobacco plantation like I did here for a TV program, Nova, where they wanted to show the history of soil in North America in 5 minutes or less. What I thought of was going to a tobacco plantation, digging a hole, and then going into the forest that had been allowed to regrow with native vegetation for 120 years on an abandoned farm next door, and compare the soil. So it's the same geology, it's the same climate. What's different is how the land has been worked and managed. The difference is the human dimension. Now, one of these soils, I would argue to you, is a healthy, fertile soil. The other one is not. Can you guess which one came from the tobacco plantation? Yeah, it's the one that looks like khaki-colored beach sand. And it is beach sand. It's just 10-million-year-old beach sand. But soil is supposed to have organic matter in it as well. And that darker one, the difference between these two soils is 100 years worth of organic matter additions by the native forest. That darker color is carbon that's been put back into the soil, and it's the only way you can keep growing tobacco. Well, it's difficult to keep growing stuff in the degraded soil. So the loss of organic matter is a big deal in soil fertility. The loss of the soil itself is as well. And in researching that dirt book, I actually tried to compile all the data I could find on the rates at which agricultural soils are eroding and how fast soils are being built. And I'm going to boil that down to a single slide. All the data is in the Proceedings of the National Academy of Sciences in a paper I published there back in 2007. And this boils it down to a single table, though. What I've got are measurements on the left, different kinds of measurements. On the right are the average or median values. And the numbers in parentheses are the number of peer-reviewed academic studies that were averaged to create the number on the right. So these are thick, fuzzy glasses of a geologist looking at a complex problem, but this is what we do. We try and simplify things. That red number up there is the average erosion rate globally, as far as I can tell, for tilled soils, for conventionally managed or plowed fields. And it spans everything from the developing world to sort of large industrial farms in the developing world. The average rate of soil erosion, as far as I can tell globally, off of agricultural fields is about 1.5 millimeters a year. That's another really small number. Your fingernails grow 10 times faster than that. The San Andreas Fault moves 10 times faster than that. These are not things that are easy to observe. But they're really important because they play out over time. And if they're consistently maintained, the difference between that red number and those blue numbers below really matters. Rate of erosion under native vegetation is about 1/100 of a millimeter a year globally. The rate of global soil production is another several percent of a millimeter a year. It's really slow. It takes centuries to make an inch of fertile soil, if not millennia in some places. The long-term geological average rate of erosion on the continents is pretty similar to that erosion rate under native vegetation and the soil production rate. And there's a reason those things balance. Our firsthand experience is that most places we go in the world, the hills are covered with soil. If they were not in balance, we'd either have a planet that was more like Mars if erosion was faster than soil building, or we'd be buried under dead stuff if stuff never decayed and rotted and disappeared, and if soil was building really fast. The bad news, of course, is the difference between that red number and those 3 blue numbers in the middle. Long-term soil erosion off the land we depend on to grow our food is radically out of balance with the rates that soils are produced. The good news lies in that lower number. That's the erosion rate under no-till agriculture from a 10-year-old compilation. I could probably get more data behind this today, but that blue number at the bottom is much closer to the blue numbers in the middle. The good news, of course, is that we know how to farm without losing the soil as a physical body. The bad news is it's called alternative agriculture. Now, I've given you the numbers already that you can do kind of a back-of-the-envelope calculation for how long an agricultural civilization ought to last. This is the kind of thing that geologists like to do over lunch with their graduate students. And that net erosion rate of about 1 millimeter a year, and I'm being conservative, I could argue for 1.5 millimeters, of a difference between the rate of soil loss under conventional agriculture and the rate of soil building, you could strip off a 0.5 meter to 1 meter thick hillside soil, a 1 to 3 foot thick soil, consult the UN Global Database, that's typical around the world. That would only take about 500 to 1,000 years. One of the things I learned in researching the dirt book is that's approximately the lifespan of most major agricultural civilizations, with some really big and important exceptions that I hope you're sitting there going, but about. And those civilizations are things like along the Tigris and Euphrates, along the Nile, along the Indus and the Brahmaputra, and the big rivers of China. What do those things all have in common? Those civilizations developed on major river floodplains. And the answer to the conundrum that I've just posed, is in that word, floodplain. Because what happens on a floodplain? Sedimentation, it floods, and the floodwaters don't just have water. They also have sediment in them. And what's the size of a grain of sand? A single grain of sand. It's a millimeter or two. What's the long-term average rate of erosion off of agricultural fields? Right in that sweet spot. If you could deposit a single grain of sand on an agricultural field, or preferably a few grains of silt, you can replace the long-term agricultural erosion that's lost from plow-based agriculture. Therein lies the conundrum of how you could sustain societies for a long time on major river floodplains. So back to the problem of erosion on outside of floodplains, which most of the world is. Is soil restoration possible, or are we sort of doomed to repeat the cycle of ancient civilizations that lost their topsoil and are in the condition that you see today in places like Libya and Syria? And if you're curious about the connection, read the Dirt Book. There's Roman tax records about great harvests in Syria and places that today are in major crisis. So can we reverse soil degradation? This is something that I actually learned very close to home, that the answer, fortunately, is yes. Because as you might imagine, I could be a bit of a pessimist if I just stopped where I ended on the last slide. But when I was finishing writing the Dirt Book, my wife, who's a biologist, was busy restoring our yard in North Seattle. We bought a place that had soil, and we wrote about it in The Hidden Half of Nature, the book that Ann and I wrote together. And the soil in my right hand, on the left of the screen, there's the soil that we started with when we cleared a lawn off because Ann wanted to create a garden, because that is her passion and her hobby. And it had about 1% organic matter, and there wasn't a single worm in our yard that we could find when we pulled that lawn off. It was an old-growth Seattle lawn, 6 inches of tangled roots, no life. The soil in my left hand on the right-hand side of the screen is the soil that we have today. It has about 10% organic matter, and it took about 10 to 12 years to essentially make that transformation, a little less than 1% a year increase in organic matter. It's incredibly fertile. We have a wonderful garden that she wanted today. So how did we do this, and how do we do it so fast? This is the process that turned me into an optimist, because I just told you about a long-term story of land degradation that took centuries to play out, and turned it around in our yard in a decade. That gave me hope. So what was the key? The key, it turned out, as we looked into it and started to understand the processes, because Ann and I are both kind of why people. We want to understand how things work. And you'd have to get 900 geological erosion rates out of the library for that last slide, the slide I showed you earlier. You have to be a data geek to actually do that. We wanted to understand how it was that the composting and mulching that Ann was doing in our yard, which is really the only thing we did to build the fertility in our yard, resulted in such a change in our soil. And that led us into the world of the rhizosphere, the zone around the roots of plants and the exchanges between plants and microbes that are happening in what we call the hidden half of nature, the out-of-sight world below our feet. And we learned that the rhizosphere is a biological bazaar where microbes and plants trade nutrients, metabolites, and exudates. This is stuff that we were not taught when we took graduate-level soil science classes when we met those many years ago. So what's happening? That blow up in the middle is the root of a plant coming down in the rhizosphere. The purple zone is the rhizosphere, just to show you the zone of life around the root of a plant. And if you want to find a zone on this planet that's dense, thick with life, look in the rhizosphere. That's where you'll find a lot of it. And those plants are pushing out of their roots things that are known as exudates, because they're exuded out of their roots, and they'll take up to 30 or 40% of the carbohydrates, or the carbon that they are capturing through photosynthesis, turn it into compounds. They push out the roots. What are they pushing out? Things like carbohydrates, sugars, proteins. There's even a paper that came out documenting plants pushing lipids, fats into the soil. Carbs, proteins, and lipids. What does that sound like? Food. Why would a plant push food out into the soil instead of using it to build their own bodies? Well, they're feeding the microbes that are in the soil, the fungi that will basically partner with the plants in exchange for those sugary exudates. They will go and actually prospect particular mineral elements out of soil particles and come back and trade them to the plants. And there's bacteria that live around the roots of plants that will consume those exudates, because those exudates don't make it more than a millimeter to a centimeter away from the root of a plant before they're eaten by something. And what does everything do with things that they eat it? They metabolize it, turn it into something else, and excrete it from their bodies. Microbes are no different. What kind of metabolites are microbes producing in the soil? This is where Ann and I started to go, wow, this is really cool stuff. Wish we'd been taught this. But this is what journals are for, right? You can actually go learn it on your own. They're producing things like plant growth promoting hormones. They're producing compounds that promote the health and growth of the plants that are producing the exudates. These are two-way streets. They're symbioses. And that leads to a different way to think about the nature of what a plant eats, the plant diet. Because we all know that you could grow, large crops in degraded land. And one of the reasons that such intensive fertilizer use characterizes the world today is if you go back and look at the degradation of land under plow-based agriculture that I talked about in the dirt book, you can re-stimulate that land to produce large harvests if you fertilize it with major elements, the N, P, and K that we know today that dominates our world of fertilization. But what happens to a plant that gets all the macronutrients they need? They don't invest so much in the root system. They don't invest in the exudates, because they're essentially spoon-fed what they need for growth, not necessarily for health. So they get fewer of the mineral micronutrients from the fungi, they get fewer of those beneficial microbial metabolites, and you can run this experiment for yourself in any cornfield in the central part of this country where you have a regenerative farm, which I'll talk about in a minute, and a conventional farm. Just try and pull the corn up by the roots. The ones that are grown in poor soil come right out. The ones that are grown in healthy, fertile soil with lots of organic matter and soil life have much thicker roots. They're harder to pull out of the ground. Because if you have a plant that's grown in an organic matter-rich soil that has a lot of life in that rhizosphere, they may not be getting as many of the major elements that they need, but they're getting more of the mineral micronutrients and they're getting those beneficial microbial metabolites. There's a direct connection, in other words, between soil health and crop health. And we got like 30 or 40 pages of citations in the Hidden Half of Nature book that sort of go into all that. There's a few papers that I'll share with you that have come out since then. This most recent one I like simply because of the inflammatory headline at the bottom of it, which doesn't quite fairly characterize the results that these people came up with, but it illustrates how things often get turned into, how scientific papers get advertised in the media world. They were looking at essentially the way that fertilization affected the defensive capabilities of plants, and the headline was "Fertilizer Destroys the Plant Microbiome's Ability to Protect Against Disease." And I point out the inflammatory nature of the headline, but I also want to point out that there's very real connections between the health of the microbiome in the root system, around the root system of the plants, and plants' ability to resist disease, to repel pests and pathogens, and that this connects back to agronomic practices. And therein, there is a connection between soil health and human health, which I'll try and play through as we go. Now, if we look at what's happened to the soil organic matter content around the world or in the United States, I'm going to step back then. Might want to get some tape for that. The most recent paper I can find that documents what's happened to the soil organic matter content in the U.S. is it's dropped by about 50%. That's about half. It's exactly half. The global number is comparable in terms of agricultural land, cropland in particular. We're not talking about rangeland, but there's also been declines in soil organic matter, soil carbon, and rangeland. And if we think about the organic matter content of soils as the fuel that drives the microbial engine that recycles dead stuff back into the nutrients that plants can take back up, we've basically run the batteries of our agricultural soils down by about half on average around this country. This is something that not only should be worrying, but it can be reversed. And how can I argue that it can be reversed? Well, I could basically say, well, we could just do what we did in our yard on farms. But you'd rightly go like, well, how would we do that? And like we were using composted herbivore manure from the Seattle Zoo. We were using coffee grounds. We were using things that aren't going to work in terms of large-scale agronomic applications. But I wanted to ask the question of, could you actually restore soil on farms around the world and do it rapidly? And that's what I wrote about in Growing a Revolution, the most recent book. And the two soil cores you see there, those colors ought to look familiar from the earlier slides. The one that is on your left, the one that looks sort of khaki colored, is a soil these are from Rattan Lal's experiments at the Ohio State University, where he was doing a 20-year no-till and cover crop experiment. The one on the left was what happens if you only do no-till. You don't necessarily build a whole lot of carbon into the ground, for reasons I could go in over beer later if anybody is interested. But on the right-hand side is what you get if you go no-till and you have cover crops and you add manure. If you're adding organic matter, you're doing the things to an agricultural field in the same spirit and style that Ann did to our yard. You start adding a lot more organic matter back to the soil. And so I took 6 months off from my job at UW teaching and traveled around the world to interview farmers that had already restored fertility to their land, because I wanted to ask them, well, how did you do it? And search for commonalities. And what I basically discovered in those interviews was that there was a common set of principles, which are known internationally by the label of conservation agriculture, where farmers could increase the fertility of their land and thereby match or exceed conventional crop yields using far less oil and chemical inputs, which has direct connections to human health, as we can kind of go, as we'll probably go through over the course of this meeting. So what are those principles of conservation agriculture? Well, they boil down to kind of three things, really, from what I could tell that all these farmers had in common. They used different practices in equatorial West Africa, in Costa Rica, and across North America, as you might expect, given the different technologies, economies, and crops that they were using, and climates that they're practicing in. But minimal or no disturbance of the ground, things like no-till farming, maintaining a permanent ground cover, keeping the ground covered with cover crops in between crops so that the soil wouldn't erode, but also to return carbon to the ground, and planting a diversity of crops. Why a diversity of crops? Because you can think of different plants with roots that go down to different levels, with different partnerships with the soil microbiome. We'll be extracting different mineral elements out of different soil particles. They're fairly specialized, and if you have a diversity of plants, you're getting that out of the subsoil, out of the rocks, and into the biological world where it can be turned over through the processes of growth, decay, death, growth, decay, over and over. These things are recipes for building up a beneficial, healthy soil microbiome, for restoring health and fertility to the land. You don't disturb the soil life, you feed it with carbon, with cover crops, and you grow a diversity of life. How does this play out agronomically? Well, I'll show you a couple of the farmers that I visited. This guy is Dwayne Beck from Dakota Lakes Research Farm, and he was a real pioneer in adopting organic agriculture. He's not an organic farmer. This is sort of a point I wanted to make. This problem of trying to talk fast in a half hour is things trip. He taught the people in his area to adopt no-till, cover cropping, and complex rotations, effectively those three principles of conservation agriculture, which in a system that they learned over a few decades, adding one piece at a time, liking the effect on their soil health and how it built stuff, it decreased their use of diesel, fertilizer, and pesticide by more than half. How did it save on diesel? Because by not plowing, they were driving across the fields half as much. They were using less fertilizer because they were getting soil life to actually add nitrogen to the soil. It can be very effective, but you have to do it in a way that promotes and cultivates those beneficial organisms. How did they get rid of most of the pesticide that they were using? Because their plants were healthier. When they restored health to their soil, they didn't need so much. Their plants were more resilient. So what happened to their yields? Look at the numbers. They went up. They didn't go down. This is not a question of the environment versus the economy. It's a win-win. So when I left Dwayne's farm, I asked him whether the practices he was using on farms that reached up to 20,000 acres. These were not small hobby farms. These were large commercial producing farms. He said, go visit Kofi Boa in Africa if I wanted to see how these ideas could apply to subsistence farming in the tropics. So I visited Kofi. Notice his hat. Got dirt, get soil. That's the whole game right there. What happened when he taught the people around his village to transition from their traditional slash and burn style of agriculture to a combination of no-tilling with cover cropping? Their erosion rates fell by about 20-fold. They basically kept the soil on the land. They had had a huge problem with degrading their soil and their organic matter prior to this. And look what happened to their corn and cowpea yields. They doubled or tripled. That's as good as the Green Revolution. They did this with no inputs. This is a change in thinking, a change in practices, a change for building soil health and fertility. Now, they still used some inputs, but these are farmers who you couldn't expect the Green Revolution to help because they have no money to buy fertilizer, they have no money to buy pesticide, they have no money to buy patented seeds. A change in thinking actually helped change their economy. The third farmer I'll show you is David Brandt. He's a guy from Carroll, Ohio, pictured there holding up one of his tillage radishes. He sells wheat, corn, and soybeans in the commodity crop markets in North America, but that's not all that he grows, because in between his cash crops, he grows very diverse mixtures of cover crops, like that radish. And that field that he's standing in front of, the one in the foreground is his field. The field in the background, the one with all the yellow stuff with little bits of green in it, that's his neighbor's soybean field, which is fairly sickly. And notice all the green stuff in his neighbor's field. Those are glyphosate-resistant weeds. They cover about a quarter of his neighbor's fields by my visual estimation. And David is somebody who basically thinks that his cover crops are his style of essentially micro-branching. He's growing his cover crops to feed the bacteria and fungi in his soil that then break down those cover crops and turn them into essentially fertilizer that his cash crops take up. So what about the economics of it? The county average for his areas with full tillage, 200 pounds of nitrogen an acre, 2.5 quarts of Roundup, cost people $500 an acre. With what they were harvesting in 2015 when I visited, and the price they were getting, they were losing $100 an acre. That's a bad business model, as even a geologist can tell. What David's been doing after he restored his soil, he's not tilling. He's using about 1/8 of the nitrogen, 1/5 of the Roundup. It cost $320 an acre. His yield was much higher than his neighbors. He was making $400 an acre the same year. This is when I started to turn into an optimist about this, because the economics seem to be playing out that if you turn your soil from that yellow stuff to that dark stuff, like David Brandt did, you can actually be a more profitable farmer. This shows you the soil he had in 1971 versus the one from 2014. The one from 71 is sampled, I believe, off of a farm next door that he just bought because he was able to do that. His neighbor was losing money, he was making money. You can figure out what happened. The combination of practices that seem to work, I can summarize as ditch the plow, cover up, and grow diversity. It's a recipe for feeding the soil microbiome and for enhancing the fertility of the land. The benefits you get from that, you lose yield, you can reduce the input uses, you can have higher farmer profits, you've got more carbon put back in the ground, better water retention, and it's not a question of organic versus conventional farming. Almost all the farmers that I showed you today are conventional farmers. They do not eschew chemical inputs. They just use far less of them than they used to, and they're more profitable as a result of that. Now, the connections to soil health in the last sort of 2 minutes that I probably have are something that were first, as far as I can tell, written about by people like Lady Eve Balfour back in the 1940s. Her book, The Living Soil, is well worth a read today. She intuited many of the kinds of connections that Ann and I had to go to the scientific literature to learn and harvest today. But they didn't have a mechanism back there for connecting poor soil health to poor crop health and animal livestock health. And she was arguing very explicitly for meetings like the one we are having today, where people from the medical community and the soil community would exchange ideas and study these kinds of connections together. Her book's well worth reading today. We've had long-term mineral declines in the content of our food. There's various studies that have documented this. They range from down to like 10% up to like 80% in certain mineral micronutrients, depending on the study that you look at. And it's not just in plants. It's also in our meat, in terms of the iron there showing up on the screen. There's also questions about what's happened to the phytochemicals, these sort of important, the non-nutritive compounds that are important for human health, things like sulforaphane, linalool, curcumin. How much have those changed in our foods over time as well? It's harder to get historical things on that because the minerals don't decay over time. Phytochemicals start to decay as soon as you harvest. So soil health and human health, the key issues to get to what we're supposed to talk today. The 3 issues that I think are central are how do we meet the caloric needs of the future without undermining our ability to maintain harvests well into the future. Soil health is a key component of that. How about the hidden hunger of micronutrient deficiencies around the world? There's connections to the life in the soil in terms of how minerals get into plants. And of course, there's the downside of pesticides, heavy metals, and contaminants. So a few key questions. Do conventional agronomic practices affect things like the soil microbiome, mineral micronutrient provisioning for crops, and phytochemical and antioxidant production? Well, the literature suggests yes to all of the above. And I'll flash through those pretty fast. The soil microbiome, there's a paper that came out last year. I mean, there's plenty we refer to in the hidden half of nature, but there was a new one in Frontiers of Microbiology that basically showed that organic farming systems have very different soil microbiomes than conventional systems. How does that translate? The mineral micronutrient provisioning for crops, there's a study out of the Netherlands that had clear differences in crop mineral densities between different types of farming systems. Farming practices affected that. And there's one that we ran in Seattle this summer where Ann and I took advantage of an experiment where a farmer had planted wheat for 2 years conventionally, and then the neighboring field planted the same cultivar and planted cover crops, and we measured the mineral micronutrient density after 2 years of cultivation that way. Look at the column on the right. It's the ratio of those minerals on the left in the cover cropped versus conventional. They range from 20% higher to 4 times, depending on which one you're looking at. And things like iron, things like zinc, things that are crucial for human health, were much higher. You don't change the soil in 2 years. What you can change is the biology. The biology was apparently more effective at getting the micronutrients out of the soil and into the crops. The last one, phytochemical antioxidant production. Yes, there are we're probably all familiar with the meta-studies that have looked at conventional versus organic production, and it's like an intellectual ping pong game of which is better which year. A lot of that focuses on macronutrients and even mineral micronutrients. One of the consistent results, as far as I can tell, in almost every study that's compared that, is that there are major differences in vitamins, antioxidants, and phytochemicals, that agronomic practices affect that. How much does that translate into human health? One of the recent ones looked at fruits, same kind of deal that I just advertised there. So as we get to the very end of this, I promise, we can ask 3 questions. How much does an altered soil microbiome affect the mineral micronutrient delivery to and phytochemical production in crops? And how much does that matter to human health? And can regenerative soil-building farming practices like those I showed you enhance the nutritional quality of crops and livestock? And how much do even low doses of herbicides and pesticides impact the soil and human microbiomes and thereby indirectly affect human health? These, to me, are the 3 key questions in connecting soil health to human health. And there's people who've written about this. Ann and I wrote a bit about it in The Hidden Half of Nature. Daphne wrote about it in Pharmacology. Getting more science to better think about how we connect those dots is a difficult thing that will require collaboration between people in the medical profession and people in the soil science field. I've argued for a 5th agricultural revolution in growing a revolution, and I know that we can restore health and fertility to the world's soils. The big question is, how much will that actually translate into improved human health? And again, as an author, I'll leave you with the cover of my books.